Okay, so now instead of focusing on the total population versus the population estimate for a particular like GPA where it's like you're calculating an average, well, now we're going to look at something where we're calculating an odds ratio. So I have data here for 947 people. Now, this data came from 947 people who were visiting a swimming beach where they went outside and went swimming at a beach. It was a state park beach. These are the people that I surveyed or that my research team surveyed. Are these all the people that went swimming at the beach at that particular lake that I'm making inferences about during the summer? No. These are just the 947 people that I surveyed. So anything I say about these people is only a estimate. It is not the true odds ratio. This is just an estimate when I calculate it because I didn't survey every single person who showed up at the beach. I could only survey the people who were available when I was there, who were willing to participate, who saw us, who knew we were there, who happened to be there at the time that we were there, who had the time and was, willing to stop. There's reasons why people participate and don't participate. And sometimes it's just you flat out just don't see them. We're only there, maybe in this case, we were there on about 20, I think 26 days. So there's more than 26 days in the summer. So we only got 947 people. A million people go to that park every year, and probably 100,000 or so actually use that beach during the year. This 947 is going to be making estimates or inferences about a huge reference population. So, say I'm interested in seeing whether or not people who went swimming in the water were more likely to get a disease or get sick like diarrhea. So later on in the class, I'll introduce you to how to do logistic regression and that kind of stuff. But this first part of the project or of the class was to at least introduce you to the concept of a 95% confidence interval and how to interpret epidemiological study results, because some of that should have been presented to you in an epidemiology class. So we have a way of seeing whether or not somebody had diarrhea or not because we asked them, we called them on a phone. This was a cohort study. We called them on a phone and asked them if they had diarrhea after they went swimming. We also called them here, I'm going to point, we asked them if they ever had any gastrointestinal illness when we called them, such as stomach aches, nausea, vomiting, diarrhea. If they had any of those symptoms in the 7 to 8 days after they went to the beach, they would tell us when we called them. So the number one indicates yes, they did for GI illness too. That's the variable. And then there is another variable in regards to swimming. Did they go in the water? Maybe it was, did you put your body in the water? Another variable we had was, did you put your head under the water? So head in. So that's the strongest exposure to the water. So we may be interested in seeing whether or not there is a relationship between people who put their head in the water and diarrhea. So the variable that I'm interested in is the outcome first. Did they have diarrhea? Yes or no, or stomach aches, nausea, or anything. So we can do diarrhea first. I'll do that variable as the outcome first. So there's a variable on here called diarrhea. I just have to find it. This is a big data set, so bear with me. Diarrhea 2, it's a shortened name so the variable fits in the program. So diarrhea, and then there was another variable called head in. So among those who put their head in, what was the odds of getting diarrhea? So when we do that, I see that the odds ratio estimate is 1.68 based upon the 939 people who we had data on related to diarrhea and putting their head in. Again, this 935 is our number of participants, and the 1.68 is our estimate of the true odds ratio for all of the people who went swimming at that beach, who put their head underwater during the summer in which we did our study. Did we survey every person that went to the beach? No, we did not. So all we can do is have an estimate. The estimate here is 1.68, and we're 95% sure that the true relationship in this particular model is actually an odds ratio between 0.75 and 3.73. So the true odds ratio for the beach lies between here. And since 1 is included, guess what? It's not significant. The p-value is 0.202. We're only about 1 minus 0.2 or 0.8 or 80% sure that there was a significant increased odds of diarrhea among those who put their head in the water. So this is not 95% sure. We are not at the 0.05 level or the 0.04 level where we might be 96% sure that there was a relationship between diarrhea and putting your head in the water. And if we were to do this again, maybe with a different variable, I was interested in GI illness. So did they have any stomach illness, nausea, or vomiting after putting their head in the water at this beach? So we run the model, and in this case, if they put their head under the water, we estimate that the odds of gastrointestinal illness was 2.4 times greater among those who put their head in the water compared to those who did not. So if you went swimming at that beach during that summer, we estimate that you had a 2.4 greater odds of reporting a gastrointestinal illness than those who did not put their head in the water. So if they put their head in, greater odds. So this is our estimate. It's based on 939 people. We generalize this to the whole population. So for all the swimmers at the beach during the time of our study or at this particular beach, we assume or we presume that the true odds of gastrointestinal illness among those who put their head in the water at that beach is actually between 1.1 and 5.16. So this is where the true odds happens to lie, between 1.1 and 5.16. The whole range of our estimate of 2.38, we are 95% sure, so our estimate falls in here, but we're 95% sure that the true odds falls between 1.1 and 5.16 for the huge population that's unknown to us. It could be 100,000 people. The true odds is between here and here. Since the whole thing is harmful in our estimate, it's statistically significant since the number 1 is not included. We have a p-value of 0.028. That means that we are 97.2% sure that the odds of disease among those who put their head in the water is greater than those who did not. Since this is below 0.05, it's actually 0.028. So if you did 1 minus 0.028, it's about, what is that, 97.2. So we're about 97.2% sure that there is a statistically significant harmful effect of putting your head in the water towards you getting GI illness. Is there still a chance that this is not statistically significant? Yeah, because there's a 2.8% chance that our assumption that putting your head in the water causes GI illness is wrong. So we could be wrong 2.8% of the time. So they call it alpha error. So our p-value of 0.05 below it means that we're 95% sure or more. And the confidence interval also reflects that. If the whole confidence interval is harmful, then we'll have a p-value less than 0.05. If the whole confidence interval is protective, we'll have a p-value less than 0.05. It's only when we have confidence intervals on our estimate that go both below and above 1, where we have protective and harmful, where we have conflicting results saying that, well, putting your head in could actually reduce your risk of diarrhea. And here it says, well, it could actually increase your risk by 3.7 times. So whenever we're on both sides of 1, then it's not significant. And we have a p-value of 0.202 here, which is clearly greater than 0.05.